Hi, everybody. My name is Dr. Mia Champion. I'm a senior data scientist with the AWS professional services team that focuses on advanced analytics and artificial intelligence. Today, I'm happy to be co-presenting with Bruce Hoff from Sage Bionetworks, who will be telling you about the Digital Mammography Dream Challenge and how AWS enables consortium science to accelerate discovery. Before his presentation, I'm going to be providing just an overview introduction of some of the services that some of our customers use for these types of projects. So many researchers use the AWS cloud because it offers the opportunity to be disruptive in the way that they innovate. So what do I mean by disruptive innovation? The cloud provides agile and scalable environment with bleeding-edge capability in the latest in computing resources, database resources, and other services like machine learning and Internet of Things. The cloud also provides a lot of educational resources that lower the barrier to entry so that anyone can learn what they need to know to build an advanced environment for their research projects. In addition, the AWS cloud is a lot like the electricity in your home. You can turn it on when you need it and turn it off when you don't. This allows you to experiment and fail fast without incurring tremendous costs. Researchers also like using the AWS cloud because it allows them to perform world-changing projects while enabling economic growth. So what does this really look like in real practice? Here's an example of how cloud computing has changed the way that researchers are actually doing collaborative scientific research. Traditionally, researchers sitting at their desk might have an on-premise server system attached to some shared file storage, and they would back up their analysis to disks or tape or databases. In order to perform comparative analysis to maybe their clinical data sets or genomic sequencing data, they would have to download remote public data sets and transfer these data sets to their on-premise server to do the analysis. Once they were done doing the analysis, if they wanted to share this information with a collaborator in order to enable a larger analysis of a collaborative project, they would have to actually ship those devices to the collaborator who would have to go through this whole cycle again with their on-premise servers just to do some additional analysis. So with the cloud, researchers are able to take advantage of our scalable storage solution for data storage, and also take advantage of our IAM policies for controlling who accesses the data and how they use the data on the cloud. Researchers can also take advantage of managed compute clusters that are auto-scaled to match their workload needs. Other services like the Elastic Container Service enable researchers to basically Dockerize their software applications and share the compute environments that they did their analysis in with their collaborators, which also promotes reproducibility in scientific research. So using containers, applications run more as microservices, taking advantage of shared resource bins and libraries. And they are also able to optimize the underlying operating system. This is quite different from more traditional instances where the applications are run more as monolithic stacks. The Amazon Elastic Container Service provides environment isolation and fidelity, some cross-platform versatility. Users are able to relate container clusters using task definitions, enabling them to also have shared volumes. With the Elastic Container Service, all the changes that are made are tracked. The containers are easy to deploy, and users are able to run diverse applications on shared hardware. The service supports cluster heterogeneity so that you're able to leverage different instance types for different tasks that you need to run. The service also supports some third-party bring-your-own schedulers. Deep learning solutions built on AWS benefit from many other layers in the AWS stack. We provide fully managed services for image recognition, text-to-speech translation services, as well as the voice and text chatbot services. We also have the Amazon machine learning service, which is for novice users that are not so familiar with building customized machine learning solutions, but want to run canned algorithms on their data sets that they upload to the cloud. For customers that want to customize their machine learning algorithms, we provide services like the Amazon Elastic MapReduce service, which is a bit of a misnomer now because Amazon EMR supports a lot more than just MapReduce functions. In addition to supporting a distributed Hadoop environment, it also supports Apache Spark, HBase, Presto, and Flink. And researchers also have the advantage of leveraging the Spark machine learning libraries that can run on the Amazon EMR service. In addition, the Amazon Marketplace provides our deep learning Amazon machine images, or AMIs, and these come pre-built with many frameworks that several researchers like to use for deep learning applications, and some of these are listed here. Underlying all of these layers are our fundamental infrastructure offerings, including the new GPU P3 instances, for example, that are excellent for training models. We also have the FPGA instances for delivering machine learning pipelines. I've already mentioned the Elastic Container Service for Dockerizing your models and sharing that environment with your collaborators. We have the AWS Batch Service that's great for optimizing your parameter settings. And then we have the serverless compute service, such as Lambda, as well as our compute at the edge services, AWS IoT and Greengrass, that are excellent for running inference analysis. And I just want to emphasize that in addition to providing popular deep learning frameworks, as well as a choice with operating systems, our deep learning AMIs are also available in a distributed computing environment by taking advantage of a publicly available CloudFormation template. So basically, by downloading this template, and the website is on the bottom of the slide, you can basically, by a click of a button, launch this distributed computing environment that is powered by P3 GPU instances. A benefit also of CloudFormation is that this template is provided in JSON or YAML formats so that it's easily customizable, so that you can actually customize this environment to fit your particular project needs. So recently, we released the new deep learning AMIs that are powered with the new Amazon EC2 P3 instances. Each NVIDIA GPU has over 5,000 CUDA cores and 640 tensor cores, delivering up to 125 teraflops of mixed single and double precision floating point. GPUs can be connected together by using an NVIDIA NVLink 2.0, running at a total data rate of up to 300 gigabits per second. And as I mentioned, many of the popular deep learning frameworks are also prepackaged in these new release deep learning AMIs, including Caffe2, the Microsoft Cognitive Toolkit, MXNet, PyTorch, TensorFlow, Theano, and more. So Apache MXNet is particularly well suited to the modern technology trends of multiple programming languages within an organization, IoT or mobile web deployments, as well as parallel computation for model training. MXNet is simple syntax. It supports multiple languages, many of which are written at the bottom of the slide. It's highly efficient for executing models even on mobile or IoT devices. And it exhibits high performance with near linear scaling across hundreds of GPUs. And this is actually the benchmark study that shows the data from that. And this was actually done, as you can see, with the older P2 GPU instances. And still, it was seen that the throughput rose by almost the same rate as the number of GPUs used for training, with a scaling efficiency of approximately 85%. So we expect that the performance with the new P3 instances will be even better. Gluon is a machine learning library that was developed through a collaboration between AWS and Microsoft. It's presently available with MXNet and will soon be available with the Microsoft Cognitive Toolkit. It's a developer-friendly, high-level API that allows for seamless switching between static and dynamic computation graphs for deep learning models. Dynamic networks can be modified during training without any compromise on performance. And there's an extensive Gluon Model Zoo API that provides predefined and pre-trained models to help bootstrap machine learning applications, and many of those are listed at the bottom of the slide. Okay, so how can these AWS services be used to enable consortium science? So here's just an example of an architecture that some of our customers have used where data scientists develop custom Dockerized machine learning algorithms taking advantage of the Elastic Container Service. They may also take advantage of another service, Code Pipeline, to integrate to continuous change integration and versioning using a source repository, and also take advantage of a test and deployment manager, as well as an image build service before they push to the Amazon Container Image Repository. The Elastic Container Service also manages all of the infrastructure provisioning so that users don't have to worry at all about doing that manually. In addition, data scientists can upload their data sets to an S3 bucket and use Lambda to trigger a function that can start ECS tasks that can fetch and process Amazon SQS messages. And then the Amazon ECS service can provision the compute clusters to actually execute the analytical jobs. Once they're done, the outputs can be delivered back to an S3 bucket for collaborative analysis. So this is just one example of a way that researchers can architect this type of solution. But to talk to you specifically about the architecture that Sage Bionetworks used, which is a bit different, I want to turn it over to Bruce Hoff.
Thank you. Yeah. Well, thank you, Mia, and thank you for AWS for inviting me to come today. Really excited to talk about what we're doing at my company, Sage Bionetworks. So Sage Bionetworks is a nonprofit located in Seattle, just down the street from Amazon. And my organization addresses a number of inefficiencies in data-intensive disease research. Pardon me. So first of all, and to give you some examples, just kind of motivate why my organization is there and what we're trying to do. Reproducibility is crucial for scientific advancements. But data-intensive disease research, like genomic disease research, has historically been difficult to reproduce studies because they often fail to accurately track things like what version of a large data set was used to come up with the results, the details for data pre-processing and cleansing, or the specific parameters or version of an analysis tool, a statistical analysis tool. So in fact, people have looked at publications and got the data that was used to derive a statistical result, and were not able to come up with the same result as the authors in a peer-reviewed paper. Another example, scientific research can often benefit by extended multi-institution consortia, but the raw data, analytic processing, and derived results from one lab need to be aligned and made consistent if the contribution of one lab is to be able to be used by the other labs in the consortium. Another example, patients are willing to share their long-term experience with their disease and the drugs that they're taking for their disease with researchers. But traditionally, to do that is done in the form of a clinical trial, which are very expensive, and the information collected in such a trial is only owned and used by the organization that put the trial together, not necessarily by all the scientists in the world. So all of these are opportunities to streamline the informatics of disease research. So Sage Bionetworks is a nonprofit hub for scientific collaboration, promoting open science, consortium management, disease-specific mobile applications, and public challenges in disease-related data analysis. So we provide an open software platform for doing data-intensive disease research. And we work with funding agencies and journal editors to raise the standard for openness for scientists that they fund and publish. We serve as a hub for these multi-organization consortia, helping to organize data and analyses that each contributes to the others. We create mobile apps in a variety of disease areas so patients can share information with researchers, and we ensure that the data sets are freely available to qualified researchers. We don't silo the data that we collect. And something I'll be talking about a lot today is we organize open data challenges in predictive modeling, requiring participants to share their approaches with the community. And then across all of these efforts, we provide governance oversight to ensure that human data is shared ethically and legally. So some examples, if you're not working in this field, why we need open science. So just a few examples I picked for this talk. In 2012, Amgen scientists published that they tried to confirm 53 landmark papers in preclinical oncology research, and were only able to reproduce the results of 11%, 6 out of 53. Another example, Bayer Healthcare reported that only 25% of published preclinical studies could be validated. And a final example, there was research done at Duke in 2006 to 2010 that led to the identification of diagnostic signatures that triggered clinical trials to begin, and then the research was deemed statistically flawed and the trials had to be stopped. So to support open science, we at Sage Bionetworks have developed a computational platform for researchers to come together and share in greater detail the data they're using for the research and how they're analyzing it. So we call it Synapse, and it supports, again, open scientific collaborations, enables sharing of all the resources, data, code, and results, and provides mechanisms to communicate in real time instead of only at the time of publication. So it's a place for living research projects. Since we're a nonprofit, by the way, all of our source code for our product is freely available in GitHub, as is access to the system itself. And I'm just going to run through some of the features of this platform. So in Synapse, people can create projects in which they collaborate. You can put wikis on your project to describe the underlying science. You can upload files that hold source data, process results, scripts used to analyze the data. And in the world of genomic research, data files can be very large. So Synapse is a federated data store, which uses as a default an AWS S3 bucket. And we use multi-part upload, which allows files of unlimited size to be uploaded into the system. We also allow people to use their private S3 bucket with Synapse, or you can use any compatible data store like OpenStack or any other file reference that's simply a URL. So again, federated data store with a default Amazon bucket behind it. We also have a provenance mechanism. So what you see here is a directed graph that links data and processing pipelines to results, so that when there is a result published, you can review exactly how the result was derived from, exactly what version of what data file and so on was used. We have a tabular data offering, Synapse Tables, that allow you to impose structure on data and do SQL-like queries to slice and dice uploaded data. We have an integrated Docker registry so that rerunnable data analysis pipelines can be pushed into Synapse and linked to data analysis provenance, excuse me. I'm going to be talking a lot in a minute about our open data science challenges. So we have integrated submission queues for these challenges where predictions can be submitted and scores and leaderboards published. Also, each project in Synapse has a discussion forum, and those are used both by scientists discussing the research and in the context of our open challenges, participants can communicate with each other and discuss their progress and challenges. So how did we build it? So started building it in 2010. We made the decision right up front to build it on top of Amazon Web Services. I think it's been a great decision. At the core is a set of web services behind an elastic load balancer running on a cluster of EC2 machines. And there's a published API to those web services for doing all the operations on the back end. The data persistence is Amazon RDS. We use MySQL databases and Amazon S3 for storing large data files. We use multi-AZ and backup on the RDS for redundancy. We have a number of clients that all go through the same published API. So when you're coming in through a web browser, we have a web portal. We use Google Web Toolkit that compiles Java down into JavaScript for our web portal. And the server side is, again, behind an elastic load balancer. Then we have command line clients that use the same API that wrap our APIs in popular languages for doing analytics, specifically R and Python. And because we integrated the Docker registry, you can use a vanilla Docker client to push and pull Docker images to Synapse. And then I'll also mention we have another cluster of what we call asynchronous workers. So if you have long-running tasks, like, for example, adding a big change set to a large table, another 1 million rows to your data table, that can be done that can be kicked off in a web request, and then progress can be monitored with subsequent web requests. So the jobs themselves are done by a set of asynchronous workers on yet another cluster of EC2 machines, separate from the ones that service immediate web requests. So that's the very high-level overview of the architecture for our Synapse system. Synapse is used by about 26,000 users right now, with about 700 new users every month. It might be small by the e-commerce scale, but in the scientific niche, that's a significant user base. We have 28 active consortia partnered with 22 Sage Bionetworks scientists to use Synapse to coordinate their work. And there are others using Synapse independent of the projects that are initiated by Sage Bionetworks. So there's no fee that you have to pay us or requirement to use it. And we find out that other scientists are using the system just when they come out of the woodwork to ask us a question about how to use it or give us a feature request. So, and that's what we want. We want the system to be able to be used independent of our organization. And of course, we have a number of dream challenges of these open data analysis challenges that we run per year. And we've done over 40 altogether. So now I'm going to talk more about the DREAM challenges. So DREAM is a series of life sciences, disease-centric challenges now in its 11th year. The selected problems are around data-intensive predictive modeling. In each challenge, we obtain and expose a high-value data set that would otherwise be accessible only by possibly a small group of researchers. We engage the community as opposed to just a select company or laboratory to leverage the greater pool of expertise in a given research area. On top of this, and you may have heard, there are many other organizations that have open challenges. But something that's unique to DREAM, we feel, is that we require participants to share their code and document their algorithms, and we make the results reproducible and extensible so that later researchers can build on top of what's been done. So when a challenge is over, it doesn't mean that that's the end of that line of research. We make everything that came out of the challenge available for subsequent research. This slide was compiled a few years ago to quantify the impact of DREAM. At the time, there were 32 challenges had been finished, involving 50 partner institutions, over 5,000 registered participants. It's impacted 10 international conferences, including 2,500 attendees, over 100 publications using the data from DREAM challenges, 25 journal articles, and the list goes on. So we feel there's been a significant scientific impact of this effort. This is my own personal spin on the DREAM challenges. I keep coming back to the parable of the stone soup, where you begin with a cauldron of boiling water that doesn't offer much sustenance, but people come and contribute a small amount to the pot, and in the end, you have a very rich stew. And it strikes me that that's how each of our challenges has come to be. So someone will approach DREAM with an idea for a challenge, and they provide the scientific leadership in a specific domain. And then someone else may donate a high-value data set. It may be the original group, or it may be someone else that has a data set that they weren't going to expose to the public, but we provide a mechanism for them to do that, ensuring that they're going to get a lot for their donation. We will often partner with a high-visibility, high-impact journal who promises to publish the winning algorithm, and that provides the incentive for people to participate. Sometimes, but not always, there's prize money. Again, could come from yet another organization. And then, of course, there's the community. We have hundreds or even thousands of participants in a given challenge. And what I really want to drill down on today, because this is a tech conference, are the IT resources, because the IT resources tend to be provisioned one challenge at a time. So the way that a challenge works from the technical aspect is diagrammed in this slide. So a participant shown on the left will come in and learn about a challenge, reading the wiki page on the landing project that we've set up for a challenge. After registering and agreeing to the terms of use, making sure that they're agreeing to how the human data will be used and so on, they traditionally download training data. They can do that from their browser or from one of the command line clients. They will then do some machine learning magic and create predictions that they can submit through our Synapse platform. And then on the back end, for each challenge, we create a challenge-specific scoring application that will use the same API to retrieve the predictions, compute scores based on a gold standard, and then publish those scores to a leaderboard. So the participants can see who's ahead, who's the winner. But what I want to emphasize here at the bottom is that the compute for scoring is provisioned on a per challenge basis. Some challenges require very little compute to compute scores, but for others it's very data intensive. And I'm going to be telling you a lot about the most data intensive one we've done as this talk proceeds. So the DREAM Digital Mammography Challenge. The motivation for this challenge is that out of all women in, at least in the United States, between the ages of about 25 and 65 or 70 are screened regularly every year, every 2 years for breast cancer. And out of 1,000 women screens, 5 will have an issue, but 100 will be recalled for further testing. And that further testing could be more invasive, or just the stress of knowing that something might be wrong is a big negative. So we have the goal of reducing the false positive recall rate for mammograms, of course, without reducing the true positive rate. So Kaiser Permanente Washington Health Research Institute donated 640,000 mammogram images. As far as I know, it's the largest data set that's ever been used to try to automate mammography. About 12 terabytes of data compressed. Started a year ago in November and just finished up today. Or not today, but this month. So the compute to process the machine learning models came from donations by 2 cloud providers, including a $300,000 grant in credits from the AWS Cloud Credits for Research program. And then there's a key constraint imposed by our data provider. They said that the participants may not download training data except for a tiny sample set. So whereas traditionally, we let people download data to train their models and then submit predictions, Kaiser Permanente said, we don't want people to download this data set. It's too sensitive, too valuable. We want people to participate but not to download the data. Well, how the heck can you possibly do that? So I'll tell you in a minute. So we have this evolution of the IT infrastructure for scoring in DREAM challenges. So before SAGE became involved in DREAM, there was no IT for scoring challenges. So they used email to submit predictions. Someone would monitor an email mailbox, pull up the submitted files, do something manually, compile a list of winners, and then email out their results. So a very simplistic approach from an IT perspective. Then when SAGE became involved, we leveraged our Synapse platform. We added the ability to have submission queues, automated scoring, real-time publishing of web-based leaderboards. And then the next variation is to allow people to submit predictive models. Instead of submitting predictions, we have challenges where people can submit the predictive model, having trained it on training data, and then on the IT infrastructure controlled by the challenge organizers, we run those predicted models against the withheld validation data, produce the predictions for each submission, compare to a gold standard, and score the results. But the third and final evolution is the submission of models for training, which is something that we added for the digital mammography challenge. So people crafted their trainable models and sent them to us. So they haven't seen the training data yet. We train their models on the infrastructure and give them back their trained model state, if you will. They then submit the model state or submit a inference model in a subsequent phase for scoring. So how can we do that? Well, it turns out that Docker is a wonderful solution to create a mechanism for doing this. So we added the Docker registry to the Synapse platform that I showed you in the earlier architectural diagram. We allowed the submission of Docker repository commits to Synapse submission queues. So instead of previously, you could only submit a file of predictions, now you can actually submit a Docker commit. We then use the Docker daemon running on each of a fleet of worker machines to pull images from the Docker registry and run the machine learning jobs. We use Docker run options like CPU set in memory to isolate multiple jobs running on the same EC2 machine. And for security, the containers have no network access, so they can only use the mounted volumes to read the challenge data and to write out their predictions or the state of the model, but they can't access the network, and that's how we can ensure our data provider that no one is copying the training data off to the internet. And again, there are Docker options that do that isolation. And we wrote a custom server-side agent that mounts all the devices and volumes, starts up containers, monitors execution, and reports exceptions and uploads results back to Synapse. So what does that look like when we put it all together? So a participant comes in, registered for the challenge, retrieves the tiny pilot data set that's not sufficient for machine learning, but just lets them get a feel for what is the format of the data, what do these images look like. Also, since we have the integrated Docker registry, we have base images that work in our challenge. So they can, if you want, you could retrieve one of these base images and just submit it, and you'll see that it runs, everything gets wired up right, and you'll get a result back. So it gives them a nice starting point so they can quickly become productive. They then create their own trainable model, submit the trainable model, and on the back end, we retrieve the Docker image, we run the trainable model, having mounted the training data, and we upload the Docker logs periodically, which the participants can monitor to make sure that everything's going okay. They have the option of canceling a job if they don't like the convergence rate or something. And then at the end, we upload the model state, which they then retrieve, and they can repeat this over time until they like the convergence of the machine learning model. They then create an inference model that they submit to the challenge. On the back end, we retrieve the Docker image, we run against the inference data, upload the predictions, well, we compute the predictions, and then we compare the predictions to the gold standard, and we upload the score. And the participant then receives the score and sees how they do compared to other participants. So I will tell you more about the infrastructure that we're using to process the submissions, which include using the GPU EC2 instances and AWS's Elastic File System. Okay, so provision compute for machine learning jobs. To support the intensive deep learning approaches, we use the AWS P2 EC2 instance type, which features the NVIDIA Tesla K80 GPU. We ran 2 models per EC2 instance at a time, giving each half the CPU, GPU, and memory on that machine. And we found that the AWS Elastic File System is an excellent way to mount the digital image data onto a scalable fleet of GPU hosts. So the bandwidth of EFS, I mean, it looks like NFS share. That's the interface that you see as a user. But they did a very nice job in making it scale up. So if you add 10 times EC2 machines, all reading the same image data at the same time, terabytes of image data cycling through to do machine learning, it scales up quite nicely, I have to say. They didn't pay me to say that. During the challenge, the most expensive part of the services that we used were these GPU instances. So we used the P2 8x large instances, and during the challenge, those cost about $173 a day. And it was very interesting that during peak periods when we received a flood of submissions, to work through the backlog, we scaled out to spending about $6,000 a day out of our $300K grant. So of course, there's no real money, fortunately for us as a nonprofit, changing hands. But that just gives you, I only mention this to kind of give you a little color and to give a feel for how we're able to very easily scale out to a large fleet of servers to process all these jobs. And then at the end of the big flood of submissions, we could scale back down. In a moment, I'll tell you more about the results of the challenge, but I wanted to include a few technical notes for those of you who are planning to use specifically GPUs with Docker containers on EC2. So when you use the NVIDIA GPUs on an EC2 instance, you install, among other things, user libraries. It's part of NVIDIA's set of low-level drivers that are tightly linked to the exact version of the GPU on the machine. But the higher-level applications are not so tightly linked. So it's very important, if you want your Docker images to be portable to a later version of a GPU, to keep them separate from the user-level libraries. So the libraries have to be installed along with the GPUs on the host machine and not in the Docker containers. Again, if you want to be able to use those images on slightly different versions of the NVIDIA libraries. So NVIDIA has provided for free a tool called NVIDIA Docker. It has 2 parts. There's a microservice that runs on every host that you can make calls to interrogate what is the exact version of GPU that's used on the host, how many GPUs there are, and where are the libraries on the host. And then there's a client side that wraps the Docker command line client. And when you say Docker run, it will add all the necessary settings to mount the GPU devices and the user-level libraries into your container so everything works correctly. In the digital mammography challenge, we used the service part, but we wrote our own agent in Java to start and stop containers. So we basically rolled our own client side of NVIDIA Docker, but the server side was very valuable. So if this is something you need to work through, I put the link at the bottom of the slide, and I encourage you to go read NVIDIA's site about how to do this. GPU monitoring. So when you have a fleet of machines, of course, you have to monitor them. NVIDIA has an NVML library that is very powerful, reporting everything from the memory used in the GPUs to the temperature. There are Python packages that wrap NVML, and there are Python packages for AWS CloudWatch. And putting it all together make it very easy to send GPU metrics to the AWS console with just a few lines of code. And if you go to this GitHub repo, you can see just a short script, like 40 or 50 lines, that pull those two libraries together and publish GPU metrics to AWS CloudWatch. And so we use that in the challenge to keep an eye on how our participants were utilizing the GPUs that we're providing them. Okay, so machine learning and the digital mammography challenge. So we provided working containerized sample submissions, as I mentioned earlier, based on the Caffe and TensorFlow frameworks, which we were told are among the most popular. And again, people could go into Synapse, they can read all about the challenge, then they can go over to the Docker tab and see Dockerized algorithms for pre-processing image data and for running Caffe and TensorFlow. And they could put it together, send it to us, and they'd have a running submission. We had over 1,200 registered participants from all around the world. And the timeline went something like this. We had 3 5-week leaderboard rounds. We took 50% of the data that Kaiser Permanente gave us, and we made that available for training predictive models. So again, people sent their Dockerized, there's someone opening the door behind me. People sent their Dockerized models in, and we trained them on the 50% partition of the digital mammography data. And again, as I described earlier, they get their model state back, and they can do whatever they want to create an inference model from these training sessions. And then we use a 20% partition for inferring cancer state and creating a leaderboard. So at the end of the 5 weeks, everyone could see how they're doing compared to others. And we did that for 3 5-week sessions in a row. And then at the end of the 5 weeks, we took all of that data, 70%, put it all together, and let models train against the 70%, and we had the last 30% held back for, again, doing the validation of the predictive ability of the models and declaring the top performers. Each team received 2 cumulative weeks of wall time on the GPU server per round, and we set quotas for retrieving logs and model state to guard against data theft, to guard against people just copying the withheld data and saying that that was like their model state or their log file. So we use some limits on data size to keep that from happening. We tried a number of things to visualize just what are people doing, what are all these participants doing, and came up, among other approaches, with this graph. So each row in this graph is one team that's participating in the challenge. The horizontal axis is time. You can see where we kick off in November and carry through May with these 3 5-week rounds, plus the final round at the end. And then on each line, it's kind of hard to see, but the dark blue lines are the training submissions. The light purple lines are the inference submissions. The green circles are where model ran to completion with no error, and the red circles are where some error occurred. And depending on how the slide appears, you can sort of see these black bands, and then you see the big purple bands are at the end of the 5 weeks where everyone is finally done with their training and submits their inference submission, and we work through our our backlog and scale up our fleet to process all those inference jobs. And again, finally in May, we do that last round of inference submissions to work through the leaderboard. And you can also see people kind of giving up, seeing that they're not doing better than others and that their time is best spent doing other things, so they kind of give up. And then other people come in late. Some people kind of arrive late and end up doing very well and being top performers at the end. So it's just interesting to see how people choose to participate. So the results, there are two phases to the challenge. There's a competitive phase that's open to the public, followed by something we call the community phase. So in the competitive phase, I told you about the 1,200 registered participants. About 400 teams were highly active. 12,000 Dockerized models were submitted to our queues, and the thing wrapped up in May. The top performer detected a significant signal with the area under the receiver operating characteristic curve of 0.87. So if you're not familiar with that metric, 0.5 means you're guessing and you have no predictive ability, and 1 would be you're absolutely perfect. So it's pretty good. We're actually detecting a signal, but not yet as good as a human radiologist. So the long-term goal is to outdo humans, but in 6 months, we didn't outdo humans. So a little more time perhaps is needed. And an important part of the results are the participants. All the participants' models are in Synapse because that was the mechanism for submitting to the challenge. So everything's there. It's all reproducible. It can all be referenced in a later time. Participants were required to put their write-ups of their algorithms into Synapse so people could understand what approach they took. The competitive phase was followed by a community phase in which top performers from the competitive phase were invited to collaborate and see if they could work together rather than competing and do even better. So that went from the spring all the way through this month of November 2017. And we just learned a few days ago that the outcome, so you'll be hearing for the first time what the outcome is, the community phase did incrementally better than the competitive phase. We were hoping for a big improvement. It ended up being a very small improvement. So continued work is needed. All the details are published in Synapse, and I have the link there for you if you want to read more about the specifics of the machine learning algorithms, the approaches that were taken, the laboratories that did the best, and so on. So just have a couple minutes before wrapping up. So I just want to drive home the point that community science doesn't end when the structured challenge concludes. So we have ongoing access to data from completed challenges. We organize these multi-institution consortia to help scientists collaborate, and we have studies using disease-specific mobile apps. So just a couple, without going into depth, I want to give you a sense of the scale of some of the consortia that SAGE organizes. So the TCGA Pan-Cancer Consortium includes 248 researchers from 28 institutions with many core projects, thousands of data sets. And just a laundry list of other consortia and collaborative projects that we're involved in. And I want to take a moment to mention the mobile health effort that SAGE is involved in, where we have 20 different research studies, each in a different disease area, like Parkinson's disease and breast cancer and so on, where participants download a mobile app onto their phone and they take surveys, they do tests, like in Parkinson's, to see how still they can hold their phone. We can use accelerometers to actually track the progression of the disease. So all that data is funneled into a backend database, again, built on AWS infrastructure, and we make it available to qualified researchers. So my last slide, I just wanted to acknowledge some of the people that were involved in all of this work. So Gustavo Stolovitsky from Mount Sinai School of Medicine is the founder and director of DREAM. Thomas Schaffer, who works for Gustavo, was one of the key IT people in the Digital Mammography Challenge. Justin Guinea was the director of the challenge. Mike Kellen is my boss, who's responsible for all the IT work at Sage Bionetworks. Thomas Yu is another key person in the DM challenge. Number of institutions that were all involved. The Laura and John Arnold Foundation donated over $1 million in prize money, for example. The list goes on, and not the least of which was Amazon Web Services. But there are many more than I can fit on the slide. Again, you have to think about that stone soup with many individuals and organizations coming together to make these challenges happen. So I encourage you to go to the webpage of our challenge, and you'll see a more complete list of the people who were involved. So with that, I'll wrap up. Thank you, and invite you to ask any questions for me or Dr. Mia Champion.